Welcome back to Nick's Algebraics. Today we're going to talk about work. And as usual, the blank and filled out guided notes will be in the description if you want to follow along. So with me today, we have Random Guy.
Another random day, another random guy.
We got Dubious Guy.
Yes, it is I, Dubious Guy.
And we have a new guest, Kaboom.
I bring the boom.
So let's start with what is work?
It's what you put into making these notes.
I did put in a lot of work to make these notes. Let me start off by saying that we're not concerned here with the common meaning of the word work. I'm not talking about physical labor. So, work in physics is a measure of how much a force contributes to an object's displacement. We care about the component of the force that's parallel or anti-parallel to the displacement. So imagine you're pushing on a refrigerator and it's a very heavy refrigerator and you're pushing very hard on it and it's not moving. Yes, you're applying a force on the refrigerator, but there's no displacement. So that means there's no work done. All right. There's no work done on the refrigerator by your force, even though you might feel tired and you did, physical labor in a way. On the other hand, let's say you're pushing a shopping cart at the grocery store. So you applied a force and it's in the same direction as the cart's motion and your cart is moving forward. So that means work is done on the cart by your force because your force is contributing to the displacement. All right. So, how do we calculate work? If the force is varying and the displacement is one dimensional, it's along a straight path, then the work equals the integral of the x component of the force, assuming that the object is moving in the x direction. And we're integrating this from x1 to x2. So the initial position to the final position.
Integrals, calculus, very spooky.
Yes. So that's the work done on a particle by a varying force during straight line displacement.
And it's a scalar.
Yes, this is a definite integral. So it's just a number. So work is a scalar quantity. If the force is constant, then you don't have to do an integral. You can just do the force vector dotted with the displacement vector. And if you don't know what a dot product is, you can just do the magnitude of the force vector times the magnitude of the displacement vector times cosine of phi, where phi is the angle between the force vector and the displacement vector. All right. So that's work done on a particle by a constant force during straight line displacement.
Are we allowed to ask what the units of work are?
Sure. Let's look at this equation here. So force, that's measured in newtons. Displacement, that's meters. Cosine of an angle, that's unitless. So the units are Newton meters, which is called joules.
That's fascinating.
Yes, very important.
Nick, explain why work is a dot product instead of a cross product.
That's a great question. So we're doing a dot product because one, work is a scalar. So if you do a cross product, you're going to get a vector. Two, we're looking at how much force contributes to an object's displacement. Let's say this is the force. Let's say this is the displacement. We're looking at what component of the force is parallel or anti-parallel to the displacement. We're looking at like this, Fx. So that's where dot products come in because dot products are related to how much one component of a vector lies along the other vector.
Or you could just memorize equations and not think too hard about it.
I don't want to get too deep into like the vector dot product stuff, so we're just gonna use fs cosine phi a lot. Okay, Example 1. I had a lot of fun making this example. Suppose that a 50-gram Krispy Kreme donut is carried 3 meters upward along a conveyor belt, inclined at an angle 11 degrees above the horizontal, as it moves towards the boxing station. The donut is moved by the frictional force of the belt, and its speed remains constant. How much work is done on the donut by A, friction, B, gravity, and C, the normal force of the conveyor belt?
Do you have to pay royalties to Krispy Kreme for using their brand name?
You know, I see this as advertising Krispy Kreme, so I think Krispy Kreme should pay me. So,
Okay.
Nick, is there a reason why you chose Krispy Kreme over Dunkin' Donuts?
well, the question is, have you ever had a Krispy Kreme?
Yes, I did, in fact.
Was it crispy?
No, soggy actually.
Yeah, right, right.
Quite
Interesting.
disappointed, Nick.
Okay, well, talk to Krispy Kreme about that. Anyway, back to the problem. Let's draw a diagram. I think a picture will really help us out here. We got a conveyor belt inclined at an angle above the horizontal. So I'm going to draw a right triangle. All right, so this is the angle 11.0 degrees above the horizontal. And we got a Krispy Kreme donut on the conveyor belt. So I'm going to just draw like a box.
If it's a donut, it's round, right? So won't it be like rolling without
Is it on the
slipping?
flat? It might be on the flat side.
Yeah, it's like flat side. I don't think they're going to
Like,
put it like this and then have it like turn down the conveyor belt. Anyway, but this is it. And what forces are acting on the donut? It kind of says it in the problem. We got the force of gravity. We got gravitational force exerted by the earth on the donut. So that's mg. Yeah, we got the weight. We have
wait, you got the weight if you're eating Krispy Kreme donuts.
that's true. Yeah. We also have the normal force. So remember that's perpendicular to the surface. So that's n. And in which direction is the friction pointing?
It always opposes the direction of motion, and it's going up the conveyor belt, so it must point down the incline.
Interesting. Well, it says that the speed remains constant. Speed constant means acceleration is 0, which means net force is 0. We already have net force in this direction because of the mg.
So the friction has to be pointing up the incline to balance that out. Basically, the friction on the conveyor belt is what's preventing it from slipping down.
Exactly, yeah. So that's what it says right here. The donut is moved by the frictional force of the belt. So the donut wants to slide down the conveyor belt, but friction is stopping that. So friction is actually up the conveyor belt. Let's define our coordinate system right now. What will make our life easier? Are we going to do X and Y like this? Or are we going to rotate our standard X and Y coordinate system?
Rotate.
Yes. So I'm going to have one axis that's parallel to the conveyor belt and one that's perpendicular. So like this. Parallel and perpendicular to the conveyor belt. Let's write down our knowns. So we have that the mass of the donut is 50 grams. What do we have to do with that 50 grams?
I prefer
Make
kilograms.
it a kilogram.
Exactly. We want in kilograms. So I just need to move the decimal point back 3 places. So you're going to get m equals 0.0500 kilograms. And we also know the angle is 11 degrees. So I'm going to call that theta is 11 degrees. We also know that the donut is carried 3 meters upwards. The length of this conveyor belt is 3 meters. So that's the displacement basically. That's S. That's the magnitude of displacement. So S is 3 meters. Okay, let's do part A. We're trying to find the work done on the donut by friction. I'm going to call that W subscript F. And is the frictional force constant, or is it changing as we move along the conveyor belt?
It is indeed constant.
Yes, this is basically static friction, and we know static friction is mu s times n, and n is constant because it's just equal to mg in the perpendicular direction, and that's not changing. Friction's constant, so we don't have to do an integral. We can just do fs cosine phi. So f is lowercase f, which is friction, and then s cosine phi. I'm going to write phi sub f, so we have different phi's. We know s, that's good, that's 3. Do we know phi sub f? Remember, phi is the angle between the force and the displacement vectors. So where is the displacement vector in this problem? This is the direction of the displacement vector. It's up the conveyor belt because that's where the donut is moving.
And the angle between F and S is 0 degrees.
Yes. So we have phi f, so that's good. But the thing is, we don't know f. So what do you guys think we should do to find f?
F equals ma.
Yeah, basically, we're going to use Newton's second law. The sum of the forces in the parallel direction equals ma in the parallel direction. Since the speed is constant, the acceleration is 0. So let me actually add that right here. A parallel and A perpendicular too are both 0. So we have sum of the forces in the parallel direction. So let's break mg up into its parallel and perpendicular components. So I drew the parallel and perpendicular components of the weight vector.
So one of those components will be mg sine theta, the other will be mg cosine theta. The way that you remember which is that sine makes it slide and cos keeps it close. So mg sine, that makes it slide, so that's down the incline. And then cos keeps it close. So mg cosine theta points into the incline.
So yeah, so basically this is going to be theta. This is the 11 degrees. The net force in the parallel direction is going to be F minus mg in the parallel direction. And this equals 0 since there's no acceleration. You can add mg parallel to both sides, and since it's opposite the angle theta, we know that mg parallel is mg sine theta because,
Sine makes it slide.
yes. All right, so now we know what F is because we have the mass, we know g, and we know theta. So I'm going to plug that into the work equation. So we have WF equals F, which is mg sine theta. So I'm just going to rearrange some stuff. So mg, and I'll put the s next, and then I'll put times sine theta.
You know, like those double S's?
Yeah, the double s is kind of made me nervous, and times cosine phi f. So now let's plug everything in. I'll omit the units. So m is 0.05, g is 9.81, s is 3, theta is 11 degrees, and phi f, we said earlier, is 0 degrees because the angle between f and s is 0 degrees.
As we all know, cosine of 0 is
1. If you put this all in your calculator, you'll get that the work done on the donut by friction is 0.281 joules.
Were you careful to use degrees, not radians, on your calculator?
Yes, very careful. Okay, so that's part A. Part B, work done on the donut by gravity. I'm going to call that WG. And again, this force is also constant, so we can use Fs cosine phi. So F is mg times s times cosine, I'll call it phi g. We know pretty much everything. We know m, we know g, we know s. We can figure out phi g. So remember, it's the angle between the force and the displacement. So we have to figure out this angle right here. That angle, you can see it's 90 degrees plus this theta, right? The angle is just 90 plus 11 degrees. Now I can just plug everything in. And then if you put that in your calculator, you'll get WG is about negative 0.281 joules.
Is that G supposed to be a subscript?
Yeah, this is subscript G. Lastly, we need to find the work done on the donut by the normal force. So part C. So work done by the normal force. Again, normal force is constant, so we can just do F, which is N, times S times cosine phi sub N. What is phi sub N? What's the angle between this force and the displacement?
That is a 90-degree angle.
Good, yeah, 90 degrees. And what's cosine of 90 degrees?
0.
Yes, that means the work done by the normal force is going to be 0 joules.
It also means the unit circle was useful after all.
Yes, phi n equals 90 degrees, so Wn is 0 joules. That goes back to my definition of work. We're asking ourselves, how much does the force contribute to the object's displacement? So the normal force is not contributing to the object's displacement because it's perpendicular to the displacement. There's no component of this force that's parallel or anti-parallel to the displacement.